called neurotransmitters. Neurotransmitters are released from the end of an axon in response to an electrical spike called an action potential. When a cell receives enough of the right kind of neurotransmitter input, a chain reaction is triggered that causes an action potential to fire, and the neuron to in turn relay messages to its own downstream synapses. Action potentials produce an electric field that spreads from the neuron and can be detected by placing electrodes nearby, allowing recording of the information represented by a neuron.
Hello, everybody. So that video was not Shutterstock. That was actually Neuralink. So that's actual video from the company. So if you want to get a sense for what it's like to work at Neuralink, that video is indicative of the atmosphere of Neuralink. It's an incredibly talented team, and you're going to hear a lot from them tonight. So we're going to actually go quite into depth on what we're doing, why we're doing, how we're doing it. And I'm just incredibly impressed with the caliber of talent at Neuralink. And in fact, the main reason for doing this presentation is recruiting. So we really want to have the best talent in the world come and work at Neuralink, anyone that's interested in trying to solve this problem. And that's actually the primary purpose for this presentation. So, okay. So the why of Neuralink, just to go over it, is I think it's important for us to address brain-related diseases. Everyone, if you survive cancer and heart disease, the odds are that you will have some brain-related disorder. So it'll be like Alzheimer's or dementia. And if you don't, friends and family will for sure. And I think unless we have some sort of brain-machine interface that can solve brain ailments of all kinds, whether it's an accident or congenital or any kind of brain-related disorder, or a spinal disorder, if you know somebody who's broken their neck or broken their spine, we can solve that with a chip. And this is something that I think most people don't quite understand yet. And we're going to go over in detail how this is possible. But I think there's an incredible amount we can do to solve brain disorders, damage, and all this will occur actually, I think, quite slowly. So I do want to emphasize that it's not going to be like suddenly Neuralink will have this incredible neural lace and start taking over people's brains. Okay. It will take a long time. So and you'll see it coming. So getting FDA approval for implantable or devices of any kind is quite difficult, and this will be a slow process where we will gradually increase the issues that we solve until ultimately we can do a full brain-machine interface, meaning that we can ultimately, yeah, this is going to sound pretty weird, but achieve it with artificial intelligence. So, but this is not a mandatory thing. This is a thing that you can choose to have if you want. And this is something I think that's going to be really important at a civilization level scale. So, and I've said a lot about AI over the years, but I think even in a benign AI scenario, we will be left behind. And so, and hopefully it is a benign scenario, but I think with a high bandwidth brain-machine interface, I think we can actually go along for the ride. And we can effectively have the option of merging with AI. I think this is extremely important. And if you think about your limbic, your limbic system is kind of your primal needs and wants, and it's like where a lot of your emotions are coming from. And then the cortex is like the thinking, planning part of your brain. And I haven't met anyone who wants to get rid of either the cortex or the limbic system. So clearly they work together well. Even though your cortex is, in principle, far smarter than your limbic system, everybody wants to keep the limbic system and their cortex. So hopefully we can have a tertiary layer, which is the kind of a digital superintelligence layer. And in fact, you already have this layer. So it's your phone and your laptop, and the constraint is just how well you interface, the input and output speed. So the output speed is especially slow with thumbs these days. So you have a very slow output speed. Your input speed is much faster due to vision, but the thing that will ultimately constrain our ability to be symbiotic with AI is bandwidth. So in the limit, after solving a bunch of brain-related diseases, there is the existential, it's mitigation of the existential threat. Oh, yeah, this is the point of it. So creating a well-aligned future, that's the idea.
Composed of nearly 100 billion cells called neurons. Neurons come in many complex shapes. But generally, they have a dendritic arbor, a cell body called a soma, and an axon. The neurons of your brain connect to form a large network through axon dendrite junctions called synapses. At these connection points, neurons communicate with each other using chemical signals called neurotransmitters. Neurotransmitters are released from the end of an axon in response to an electrical spike called an action potential. When a cell receives enough of the right kind of neurotransmitter input, a chain reaction is triggered that causes an action potential to fire, and the neuron to in turn relay messages to its own downstream synapses. Action potentials produce an electric field that spreads from the neuron and can be detected by placing electrodes nearby, allowing recording of the information represented by a neuron.
We thought we'd play that twice. Like a lot of people in the audience, there's a wide range of knowledge about neurons. Some people view the brain as like this incredibly mystical thing that you cannot interface with the brain, and then some people are aware of deep brain stimulation, such as occurs for Parkinson's patients. So try to address the broad range of understanding. Neurons essentially there's that whole idea that this is often posed by philosophers, except we are a brain in a vat, and that vat is our skull. Everything that you perceive, feel, hear, think, it's all action potentials. It's all it's neural spikes, and it feels so real. It feels very real. But these are all impulses from neurons, what's called a spike. And our goal is to record from and stimulate spikes in neurons and do so in a way that is orders of magnitude more than anything that's been done to date, and safe and good enough that you can, it's not like a major operation. It's sort of equivalent to sort of a LASIK type of thing. So where you can sort of sit down, machine does this thing, and you can walk away within a few hours. And that's it. And you're not even in a hospital. So there's basically, in terms of key points that are worth taking away, the system that we designed in version 1 is capable of on the order of 10,000 electrodes. So each chip, which is 4 by 4 millimeters, is capable of 1,000 electrodes, or has 1,000 electrodes. And we think doing up to 10 is feasible. So this is in contrast to the best FDA-approved system, which is like a Parkinson's deep brain stimulation thing, which would have on the order of 10 electrodes. So the system, even in version 1 that we're going to unveil today, is capable of 1,000 times more electrodes than the best system out there. And they're all read and write. So this is really quite, for something to be 1,000 times more than what is publicly approved is quite a big difference. And this will get better with subsequent versions. Now this slide may seem a little generic, because like everything's got robots, electronics, and algorithms at this point, but not threads. So the I feel like I'm in Transcendence. Actually, I was in Transcendence. So there's very tiny threads that are about a tenth, roughly, of the cross-sectional area of a human hair. So they're extremely tiny threads. In fact, the threads that we have, like I said, even in version 1, are about the same size as a neuron. So if you're going to go stick something in your brain, you want it to not be giant, you want it to be tiny, and to be approximately on par with the things that are already there, the neurons. So this is about the size of a neuron, each thread. And then you really need this to be done with a robot, because it's very tiny and it needs to be and you don't want to pierce a blood vessel. So so each thread, the robot looks sort of basically through a microscope and inserts each electrode specifically, bypassing any vasculature, any kind of like blood vessel, and making sure that it can be inserted without causing trauma or minimal trauma. Yeah, it's not zero, but important part. You want you won't feel a thing. Yeah, anyways, obviously algorithms. So just to give you a sense of scale, this is how tiny the threads are. That is not even a big finger, that is a small finger. So these threads are just like I said, way smaller than a hair, and there's 1,000 of them. And this is what the robot looks like. It's sort of quite a complex device, but it all comes down to a very tiny point. So we want to just like you see the robot on the left, and then the what looks like the needles for insertion next to a penny, but in fact the actual needle that gets inserted is way tinier. It's that little tiny thing at where the arrow is pointing. That's actually the size of the needle. It's about 24 microns in diameter. Extremely small. It's so small you can't really even see it in the picture with the penny. And then this is your rain on uranium. No, that's not really. That's agar. So you can get a sense for the robot doing the electrode insertion. That's a very zoomed in view. So they're all very tiny, applying them very delicately, and then this is what the chip looks like. So there's action potentials. So each one of those represents one electrode. So there would be up to 10,000 of these lines. Yeah. So I guess it's always difficult to say. There's going to be there's a lot more in this presentation. So in terms of things that I think are important to bear in mind, this I think has a very good purpose, which is to cure important diseases, and ultimately to help secure humanity's future as a civilization relative to AI. The threads are very tiny, and there's a lot of them, and they're very carefully placed. And the operation on a per chip basis, it involves just a 2 millimeter incision, which is dilated to 8 millimeters, and then the chip is placed through that, and then it goes back to being 2 millimeters, and you can basically glue it shut. You don't even need a stitch. So, and then the interface to the chip is wireless. So you have no wires poking out of your head. Very important. So it's basically Bluetooth to your phone. Because we'll have to watch the App Store updates for that one. Make sure we don't have a driver issue. Updating. But the key is like this is something that is going to be not stressful. Our goal is not stressful to put in. Should work well, hopefully. We'll check it out very carefully before it becomes. And it's wireless. So this I think has tremendous potential, and we hope to have this aspirationally in a human patient before the end of next year. So this is not far. And then, as I mentioned earlier, this is the main purpose of this presentation is recruiting, and we need very talented people in all these areas. So it's a lot of very talented people are needed to make this ultimately successful. And then, speaking of talented people, let me hand it over to Max. Yeah.
Thank you. I need the clicker. The present. Thank you. Thank you. I'm Max Hodak. I'm the president of Neuralink. I remember a couple years ago when we started talking about the idea of Neuralink and that there might be a company and whether this was even a good idea. I remember my first reaction was that I wasn't sure that this actually was a good idea, that the technology was there yet. And I think Elon has this incredible optimism where he'll pierce through these imagined constraints and show you that really a lot more is possible than you really think is today. And you have to be very careful telling him that something's impossible. It better be limited by a law of physics or you're going to end up looking stupid. And so I've wanted to build a neural interface has really been like a central goal of my life for basically as long as I can remember. I think like we talk about AI being potentially the last invention that we have. I think that a high bandwidth BMI might be like really the first invention in many ways of like, it's just really like as Elon alluded to earlier, everything about your experience, your thoughts, your memories, it's all in your brain and represented in the firing statistics of action potentials. So, all right, so just what is a BMI? And we'll go through this fairly quickly, I think. So you start with hopefully a brain and a machine. The machine is just a stand-in for the outside world. It could be another brain, it could be software, it could be a robotic arm, but you want to receive energy from that world and impart through the senses like vision and audition and impart energy back into the world through things like motor control. And that language that they use to communicate, putting aside the interface hardware for a second, it's very important to understand what that is, because people ask like, oh, can I talk to my dog, or can I do these things? But it's important to understand what that language is. And that language, in the most general sense, is information. To a first approximation, everything is information. But we just consider here the information represented in neurons. And so consider two like toy neurons. So these lines are imagined action potentials. And so imagine a neuron that fires very regularly like a metronome. Like this doesn't tell us anything. There's no information conveyed in this signal. We don't learn anything from it. On the opposite end of the spectrum, imagine a neuron that fires completely randomly. This also doesn't tell us anything. This also doesn't carry any information. Now we know that these two degenerate cases are not what neurons do, because from recorded neural activity to behavior of things like a cursor of a patient or a subject that's implanted, and you correlate these, then you can build a graph that looks like this. This is a figure from a classic paper in this field, from like the academic heritage of this field from 2003. I think that actually some of the authors of this paper are in the audience today. And you can see it's the x-axis is number of neurons, and the r is the goodness of fit. And you can see that as you add neurons, the quality of the model improves. This tells us that neurons and their spike trains carry information about things. Here it asymptotes fairly quickly. That's because what they were fitting here was just 2D cursor control, which has simple dynamics. And if you have tasks that are more complicated, then you need more neurons. So the classic definition of information is a difference that makes a difference. It's just some piece of information or knowledge that tells you something. It's like a very abstract concept, but it's such like information theory is such a deep rabbit hole. If you haven't seen it before, the original paper, Mathematical Theory of Communication, is like, it's very readable. I highly recommend it. You'll start seeing information everywhere. It will totally change the way you view the world, because the world is information, as we've talked about before. And understanding information also gets this question of, well, why do you have to have an implantable device? Why don't you have EEG or a wearable or an optical thing? And the answer, of course, is like, well, these are different information carriers, and what information are they carrying? And we know that like if you open a back issue of the Journal of Neuroscience and you want to understand how some species of bird encodes sound localization or something, you'll find a discussion of spikes. And as far as we know, everything that we care about is found in the statistics of spikes. So that's what we focus on. There are other things like fMRI or EEG. These are different information carriers carrying different information, which we believe is impoverished relative to spikes. I think that's the scientific consensus. And so the question for all these different things is, well, what information is found in your carrier? We focus on spikes. That means we have to be inside the brain, because there's no ceiling that we're aware of on that with respect to that like grand vision of your perception, your thoughts, everything, like motor output, re-embodying lost limbs. And so why does that mean that you have to be inside the brain? So you want spikes. Well, people have studied, if you take a neuron and you put an electrode on that specific neuron, so you have a ground truth electrical potential of that one neuron, And then you place an extracellular electrode nearby, which is what our electrodes in the Utah array and other people are like. We're not in the cell, we're near the cells. And then you measure how far away from a neuron can you be when you know what the ground truth spiking activity is, can you no longer see the spikes? And it turns out that the answer is about 60 microns, which is like 0.06. It's very small. It's a lot less than a millimeter. So you have to be firmly under the skull. Like there's no wearable that is going to get you spikes. This is a physics constraint as far as we're aware. And so now I just want to talk about briefly that Neuralink didn't come out of nowhere. There's a long academic heritage of research here. The cochlear implant has reached millions of patients since the 50s for deaf patients. Over 100,000 patients have received deep brain stimulation for Parkinson's and essential tremor and dystonia, and now other indications. And about 20 patients have received the Utah array, which is a little 100 electrode rigid metal silicon device. And even though it has very few channels, they've been able to do some really cool stuff with it. There's videos on YouTube of brain gate patients doing things like controlling tablet computers or even texting each other through Utah arrays just from the small number of electrodes. And so many of the people on the team at Neuralink came from this academic work. I got my start working in a lab at Duke University studying how mappings between brain and like the screen space change. So if you make it so that the joystick goes, like the cursor goes sideways when you push forward instead of up, like how does the brain change that representation? So the point is that there are lots of people that have been looking at this problem from lots of angles for decades. And we're, in the greatest sense, building on the shoulders of giants here. And so the question is, why not use one of those devices? Why not use a Utah array or a deep brain stimulator implanted pulse generator? And in the Utah array case, the rigid sharp metal electrodes produce a fairly strong immune response. And this doesn't end up hurting the patient, but it does mean that you lose the ability to record single spikes over some period of time, usually between 1 and a couple years. There's also a big percutaneous connector through the scalp. So you need to plug in big external electronics, and you're never really confident that the risk of infection is gone for the duration that you have the implant. Deep brain stimulators solve a very different type of problem. They are very effective for some Parkinson's patients, but they have only a couple electrodes, and they're really geared towards injecting large amounts of current, not recording single spikes. So they're really a very different, the DBS is really just a very different type of platform for a very different type of problem. So we had to go back to the drawing board and start over to build something that met the goals that Elon laid out for us. We knew, as Elon mentioned, that whatever we built, we wanted it to be completely wireless. We didn't want any connectors or wires coming through the skin. It had to be something that would last for a long period of time, not something that you'd have to take out at 2, 3, or 4 years in. It had to have practical bandwidth. So we talk about high bandwidth or ultra high bandwidth. Like, what matters is that for the task that you're after, there is practical bandwidth that allows you to effectively do that thing, whether that's cursor control or typing or robotic arm or maybe in the future vision. And it has to be usable at home. It can't be something that you go into a clinic at the hospital for 2 hours a week and under tight supervision of technicians plug you into the amplifiers and turn it on. It has to be something that you can live with. And so 2.5 years ago, we were nowhere close to any of that. This is a photo of some of the prototypes that we've gone through over that time. So we started on the far left. That's an entirely passive board that has 64 electrodes on it and connects to connectors that go to big external amplifiers. And then we added integrated electronics with our first custom chip. That's also 64 channels. And then there was a big leap to the device that Elon showed a photo of earlier. That has 3,072 electrodes in a fully implantable package with just a USB-C port coming out. And then we took a step back in channel count because remember we have to optimize safety, longevity, and bandwidth all together. And so in order to optimize some of those other things, we moved to an easier to manufacture system that has 1536 channels and a USB-C port. And those last two are the focus of the paper that we released today. And so we've learned a lot from these. We've recorded a lot of data through these. Like these are actually used every day at Neuralink to record neural data and work with it. And they taught us a lot about the architecture that we think was the basis for our first human product that we're calling N1. And the central component of that is the N1 sensor. It's a little hermetic package. When it's fully assembled, this is missing an outer mold. It's into an 8 millimeter diameter, 4 millimeter tall cylinder. And each of these has 1024 electrodes, and we can stim and record through every one of those channels. Exploding it, opening it up a little bit, you can see there's the thin film, which has the threads that Elon talked about, which is the wisp going off to the side. There's a hermetic substrate, and then that gets welded later to a package that goes over top, and that's mated to our custom electronics. And we'll go into more detail. We'll have the technical leaders that work on each of these talk about these in more detail over the rest of this presentation. So yeah, I mean, this is just not to belabor the point. I know that Elon really hammered this in, but these things are very, very small. They're not. You can't manipulate these. This is one photo. This is not two photos joined together, and you really can't manipulate these with your hand. That part at the top is just a backing material that's surgical packaging. They're peeled off. The threads are peeled off that one at a time by the robot to place into the brain, and we had to build a surgical robot. And the first impetus for this is just you have to place these threads. You can't manipulate these threads. You need a robot. And then that grew into understanding where the blood vessels are and imaging into the tissue, and the surface of the brain moves because you're breathing and you have a heartbeat. And there's lots of complexity of dealing with this incredibly high entropy substrate. And it's not all offloaded to the robot. It's the robot's under the supervision of a human neurosurgeon who lays out where the threads are placed. Surgery is not possible without the robot. And so the N1 implant, we can place, as Elon mentioned, many of these, possibly up to 10. In one hemisphere, for our first patients, we're looking at four sensors, 3 in motor areas and 1 in a somatosensor, connected via very small wires tunneled under the scalp to an inductive coil behind the ear. And that connects wirelessly through the skin to a wearable device that we call the Link, which contains a Bluetooth radio and a battery. And this is, importantly, the only battery and radio in the implant. So if you take this off, the implant shuts off. And if there's software upgrades or security issues, it's much easier to upgrade the firmware on the pod than it is to try and change the implant. It'll be controlled through an iPhone app. You won't have to go to a doctor's office and have them have an exotic programmer to. And the first thing that you'll have to do is learn to use it. Like, imagine if you've never had arms, and then suddenly you have an arm, and you have to pick up a glass on the table. It's like not a cognitive task. You just how do you can't think your way through that. And so it's kind of a trippy experience at the beginning where, like, patients, at first it just kind of wanders around, and then they learn how to control it. And that's like it's a long process. It's like learning to touch, type, or play piano. And so for the first product, we're really focusing on 3 distinct types of control. The first is giving patients the ability to control their mobile device, because we heard from over and over again from patient groups that if you have to have a caretaker around to press buttons for you, what's the point? You might as well have them do the thing. You have to get self-sufficient using the devices on your own. And then your phone to a keyboard or a mouse on a normal computer. It'll just show up as a Bluetooth mouse or a Bluetooth keyboard, like any keyboard or mouse that you can use on any computer. And as Elon mentioned, this is a forward-looking statement. There's a whole FDA process we have to go through. We haven't done that yet. This is like, these are aspirations. But we are working as hard as we can towards our first in-human clinical study next year. And again, these are plans, but the primary indication for that will be complete paralysis by upper cervical spinal cord injury. And we're expecting that those patients will get 4 1024 channel sensors, 1 each in primary motor cortex, supplementary motor area, and dorsal premotor cortex, which are 2 motor planning areas, and closed loop feedback into primary somatosensory cortex, which is like when you type or walk or pick up a pen, those aren't visually guided movements. Your body has all these senses of where it is in space and pressure and temperature and lots of other feedback. And we think for really high fluent control, you have to provide that back to the brain for the synthetic effectors also. And of course, fully wireless and able to use it at home. We think that there's a huge difference between something that you get to use 2 hours a week at the hospital versus something that you're living with every day and your brain is adapting to as much as the device is adapting to your brain. And so to bring up the other colleagues, this team is like, I'm incredibly lucky to get to work with this team. We're going to go into a little bit more detail on, I think that decoupling implantation from the electrodes is incredibly important. The reason that you have these issues where things like these like tungsten microwires get rejected is they're stiff and they're stiff and sharp and they tear the brain, and they have to be because they have to get into the brain. And so if you can decouple the process of getting it into the brain from what is left there, where it can be much softer and have material properties like the brain and maybe be coated in things that help the brain recognize it as itself, that's really important. And then the thin film polymer leads, the threads themselves, are really cool material science, and we'll go into more detail on that. And then we'll also talk more about the chips, and then a little bit more on just the neuroscience of how information is represented in firing statistics in your brain. And so with that, I'd like to welcome Dr. Matthew McDougall.
Thanks, Max. I'm Dr. Matthew McDougall. I'm head neurosurgeon at Neuralink. When I'm not at Neuralink, I'm a brain and spine surgeon here in San Francisco at CPMC, California Pacific Medical Center. Before that, I was at Stanford, where I worked in labs that implanted and designed advanced brain-computer interfaces. I originally became a neurosurgeon because I wanted to help people live happier, healthier, longer lives. I've been humbled in practice by how powerless we are to treat many of the most debilitating neurologic diseases. People afflicted with spinal cord injury, schizophrenia, autism, and a host of other neurologic conditions have far too few options. I work with Neuralink because we, for the first time in history, have the potential to solve some of these problems. Before we get to how we get the device in, we have to talk about our guiding principle at Neuralink. It's safety. Everything we do at Neuralink is filtered through the question, will this make me more likely to want to get one? Will it make me more likely to recommend this to my family and friends? This approach impacts every design decision we make. So while for the immediate future, Neuralink's devices will only be intended for patients with serious unmet medical needs, our design philosophy is that this should be safe enough that it can be an elective procedure. So what have we done to try to make it safe? For starters, we've created very small threads. They displace a lot less tissue than the traditional methods. In my regular practice today, I routinely implant large, deep brain stimulator electrodes into the brains of my patients. They're big enough to have about a 1 in 100 chance of causing a significant hemorrhage. They displace and disrupt enough brain tissue that you can often see neurologic consequences just from placing the wire. We can do better than that. Neuralink's threads are so thin that they're difficult to see with the naked eye. They're much smaller than the width of a human hair. They're small enough that a human surgeon can't actually implant them without help. So we created help. Neuralink developed a tool that we're extremely proud of, the robotic inserter. Inspired by designs conceived of in labs here in the Bay at UCSF and Berkeley, we developed this robot that can rapidly and precisely insert hundreds of individual threads representing thousands of distinct electrodes into the cortex in less than an hour. This tool allows a surgeon to aim between the blood vessels that cover the surface of the brain with micron scale precision. The region of the brain shown in this video represents only a few millimeters of surface of the brain. As you can see, the brain's surface moves with the heartbeat and breathing. The robot tracks and adjusts for this movement. Using this tool, we can greatly reduce the risk of harming cortical vessels and causing bleeding. Here, the robot is selecting individual electrode threads and placing them into the brain in the pre-planned location with remarkable accuracy and repeatability. Using this system, we've been able to rapidly place thousands of electrodes into the cortex without causing noticeable bleeding. We also have an in-house histology team that examines brain tissue to help us choose electrode profiles and materials to help us minimize tissue damage. When you think of traditional neurosurgery, you probably think of something very invasive. Traditional surgery on the brain isn't something that patients ever look forward to or are excited about, except in the most dire circumstances. Usually a clamp is attached to the skull to keep it rigidly immobilized to the operating table. We often shave all or most of the patient's hair. Patients can end up with large visible scars. At Neuralink, we want to create an entirely different patient experience, something more like LASIK. No scars, no big scars, no hospital stays, no short procedures, no hospital stays, very short procedures, and of course in the end you get to keep all your hair. We even want this to be possible under conscious sedation. That means you can get rid of the complexity and the risk of general anesthesia, as well as many of the unpleasant side effects, nausea, sore throat from a breathing tube. To be absolutely clear, our first clinical trial patients are going to receive an experience much more like traditional neurosurgery. But our aim is to simplify the procedure, down to the injection of local anesthetic, a very small opening in the skin, a painless opening in the skull below, quick and precise placement of threads into the cortex, and then we fill that hole in the skull with the sensor closed up over it. Behind the ear, we'll make a small incision to insert the coil. We will tunnel tiny wires under the scalp to connect the sensors to the coil. That's the process. I believe that Neuralink is going to be able to provide us in the medical community with a platform that can finally enable us to treat some of these very difficult to treat diseases, also to understand them better. I hope you find this as exciting as I find it. If you feel you might be able to help us, don't hesitate to contact us. To talk more about the technology behind all this, I'd like to introduce Vanessa Tolosa, Director of our Neural Interfaces Group.
Hi, I'm Vanessa Tolosa. I lead the Neural Interface Group at Neuralink. Our team consists of engineers and material scientists who are responsible for making the probes that get implanted into tissue, the packaging for the electronics, and integrating these two components together. We also do all the testing and characterization of these parts. Before joining Neuralink, I led a neurotech team at Lawrence Livermore National Lab. There we worked on a wide range of neuroprosthetic technologies that were used both in the academic and clinical settings. I decided to join Neuralink because I saw an opportunity to take all of this exciting work that we were seeing in neurotech research and actually make them accessible to patients at a much faster time rate than what medical device companies have traditionally been able to do. With that in mind, at Neuralink, we set out to create a fully implantable neural interface with thousands of channels that are capable of single spike resolution. This device must last a long time in the body. To do this, it must be small, flexible, and made of biocompatible materials that will minimize the brain's immune response. To protect the electronics from the caustic environment of the body, it must have airtight packaging, also known as hermetic packaging. The device must also be able to both record from and stimulate neurons. This is essential BMI. Finally, the manufacturing process must be scalable and capable of making micrometer-sized features consistently. Currently, there are no research or commercial devices that meet all of our requirements. So we built one out of microfabricated thin film polymers. Just like in semiconductor chip manufacturing, we use a layer-by-layer process that generally consists of 3 repeating steps. We're either always depositing material, patterning a material through photolithography, or etching away a material. Depending on the complexity of the design, these steps could be repeated over 100 times. And to make things more challenging, we are limited to materials that are... In our current design, we have a 3-metal layer process that results in a 5-micron thick and 10 to 40-micron wide probe. To give you an idea of how small this is, red blood cells have a diameter of about 8 microns, and an average strand of hair is about 100 microns. Yet in this small footprint, we're able to fit our electrodes, our wires and the insulation for each of those wires. With microfabrication, we can drive features down to the size of an electron beam. So this is great because we want to make our probes as small as possible. Essentially, we want it to be invisible to the brain. But there are other factors that limit the size of our probes. For example, as we make the wires smaller, it increases the resistance of those wires. And as the resistance increases, it makes it more difficult for us to separate our signals from our noise. Similarly, there are other technical challenges and trade-offs that are related to higher channel counts and manufacturing yield, electrode size, and material and tissue safety. At Neuralink, we have an incredible team that's been tackling these challenges and have been able to make high channel count polymer probes. And this image is a silicon wafer that holds 10 of these arrays, these polymer arrays. In this design, each of those arrays has over 3,000 channels. So what that means is in this one wafer, we've manufactured over 30,000 electrodes and over 30,000 insulated wires. This is something that can't be done with the way current medical devices are being made. That rainbow effect is caused by the small feature sizes on these devices that are interacting with the nanometer size wavelengths of light that are reflecting off of them. If you were to zoom in on the ends of one of these arrays, you'll see this region where we put all of our electrodes. So each of these vertical filaments that end in a loop is what we refer to as a thread. And each of these threads can be placed independently into the brain using our robot during surgery. This design is called linear edge. It's one of over 20 designs that we've made for our R&D work. We've progressively been increasing the number of electrodes per thread without significantly increasing the width of each of these threads at the base. We've been able to do this by adding layers and reducing the sizes of the wires down to as small as 350 nanometers. This is less than the wavelength of visible light. Because we're using a lithographic process, essentially if we can draw it, we can also make it. So on one end of our probes are the electrodes. On the other end are where we
All right, welcome to the Neuralink product demo. I'm really excited to show you what we've got. I think it's going to blow your mind. So the primary purpose of this demo is actually recruiting. So I'm going to emphasize this at the beginning and then again at the end. We're not trying to raise money or do anything else. The main purpose of this is to convince great people to come work at Neuralink and help us bring the product to fruition, make it affordable and reliable, and such that anyone who wants one can have one. And so I want to emphasize the purpose of Neuralink. Like, what's our goal? Our goal is to solve important spine and brain problems with a seamlessly implanted device. So you want to have a device that you can basically put in your head and feel and look totally normal, but it solves some important problem in your brain or spine. And the reality is that almost everyone over time will develop brain and spine problems. These range from minor to very severe, but if you live long enough, everyone's going to basically have some kind of neurological disorder. And these range from memory loss to brain damage. But the thing that's important to appreciate is that an implantable device can actually solve these problems. I think a lot of people don't quite realize that. But all of your senses, your sight, hearing, feeling, pain, these are all electrical signals sent by neurons to your brain. And if you can correct these signals, you can solve everything from memory loss, hearing loss, blindness, paralysis, depression, insomnia, seizures, anxiety, addiction, strokes, brain damage. These can all be solved with an implantable Neuralink. This is an extremely fundamental thing. I think a lot of people don't quite understand that. The neurons are like wire. The neurons are like wire. The neurons are like wiring, and you kind of need an electronic thing to solve an electronic problem. So current medical research, we'll just go through what is the state of the art in medical research, and then what's the state of the art in what consumers or people in general can get. So the current medical research has shown that you can read neurons in a human's brain. So there's something called the Utah array, which has about 100 channels per array. But it's like, kind of like it's a bed of rigid spikes that's literally inserted with an air hammer. So that's slightly discomforting, I think. And there's wires and a box on your head. And so it's some infection risk. And obviously, it will look pretty weird if you walk around with boxes on your head. And in order to use it, you have to have an expert medical professional there. And it's only been done in a few dozen people. So, but it is served as an important proof of concept that this can be done. So we did want to point this out and show that this actually does work. It's just not something that the average person could use effectively. And then in terms of what is currently available, there is something called deep brain stimulation, where they put electrodes, a small number of electrodes, in your brain, and will actually zap your brain with an electric current. And it's valuable for its uses, but it can't read or write high bandwidth information. I would say this is sort of a bit like sort of kicking the TV, which does work, but not always, and it has limitations. Nonetheless, this has greatly helped over 150,000 people, and it's actually, despite being somewhat of a brute force approach, it has been very effective for a lot of people. And this is what's currently available. So we want to radically improve this by multiple orders of magnitude. Improve it by a factor of 100, then 1,000, then 10,000. So going into the Neuralink architecture, what we've done over the past year is dramatically simplify the device. So we about a year ago, we had a device which had multiple parts, including a piece that it had to sort of sit behind your ear, and it was complex, and you wouldn't still look totally normal. You'd have a thing behind your ear. So we've simplified this to simply something that is about the size of a large coin, and it goes in your skull, replaces a piece of skull, and the wires then connect within a few centimeters or about an inch away from the device. And this is sort of what it looks like. So, yeah. This is our little device. It does, that thing at the bottom is just to hold the threads in place because they're just like little fine wires. I mean, frankly, to sort of simplify this, what we're, I mean, it's more complicated than this, but it's, in a lot of ways, it's kind of like a Fitbit in your skull with tiny wires. So, and it's, yeah, so our current prototype, version 0.9, has about 1,000 channels. So that's about 100 times better than the next best consumer device that's available. And it's a 23 millimeters by 8 millimeters. It actually fits quite nicely in your skull because your skull is about 10 millimeters thick. So it fits, it goes flush with your skull, it's invisible, and all you can see afterwards is that there's a tiny scar. And if it's under your hair, you can't see it at all. In fact, I could have a Neuralink right now, and you wouldn't know. Maybe I do. So, and it's also got all the things that you would expect to see, the sensors you'd expect to see in a smartwatch or a phone, like inertial measurement, temperature, pressure. So there's actually a lot of functions that this device could do related to monitoring your health and warning you about a possible heart attack or stroke or other damage, as well as sort of convenience features like playing music. You can do a lot. It's sort of like if your phone went at your brain or something. Yeah, maybe that's not a great analogy. Anyway, so it's also inductively charged. So it's charged in the same way that you charge a smartwatch or a phone. And so you can use it all day, charge it at night, and have full functionality. So you would really, you know, it would be completely seamless, and yeah, no wires. In terms of getting a link, so that, you need to have the device, a great device, and you also need to have a great robot that puts in the electrodes and does the surgery. So you want the surgery to be as automated and as possible, and the only way you can achieve the level of precision that's needed is with an advanced robot. So we're really looking for great people who can help develop both the device and the robot. And we feel confident about getting the link procedure, the installation of a link, done in under an hour. So you can basically go in the morning and leave the hospital in the afternoon. And it can be done without general anesthesia. So in terms of getting a link, like I said, it's essentially you open a piece of skull, you remove about a coin-sized piece of skull, and then the robot inserts the electrodes. We'll talk more about that later. Then the device replaces the portion of skull that was removed, and we basically close that up with actually super glue, which is how a lot of wounds are closed, and then you can just walk around right afterwards. It's pretty cool. So this is our surgical robot. And we actually ultimately want this robot to do essentially the entire surgery. So everything from incision, removing the skull, inserting the electrodes, placing the device, and then closing things up and having you ready to leave. So we want to have a fully automated system. And to be clear, this robot does actually work. We've used it for all of the implantations. So this shows you at sort of close-up view, which I think is actually not too gruesome, of the electrodes being inserted in the brain. And if you look closely, you'll see that it's a little counterintuitive that if the electrodes are inserted very carefully, that there's no bleeding. And so if you have very tiny electrodes, and if they're inserted very carefully, so that the robot actually images the brain and makes sure to avoid any veins or arteries, so that the electrodes can be inserted with no noticeable damage. So you will have no noticeable neural damage in inserting the link. Yeah, like you sort of think like if you stab something with a wire, surely it will bleed, but actually at a really small scale, it does not. So does it actually work? And what I'm excited to show you, I call it like the three little pigs demo. And if our animal handlers, we're bringing out the pigs, and what we're going to show you is well, I'll walk right over and show you. So what we have in pen number 1 is Joyce, and she does not have an implant. Obviously healthy and happy. We're trying to get Gertrude out. And this is how you know it's a live demo. She's like, yeah, she's trying to eat something in the corner of her pen. Come on, Gertrude. Let's go. Snacks are this way. Oh, man. All right. We'll wait. We'll give Gertrude a second, and we'll move on to Dorothy. Sometimes the pigs are a little shy. So here's Dorothy. And in the case of Dorothy, Dorothy used to have an implant, and then we removed the implant. So this is a very important thing to demonstrate is reversibility. So if you have a Neuralink, and then you decide you don't want it, or you want to get an upgrade, and the Neuralink is removed, is it removed in such a way that you are still healthy and happy afterwards? And what Dorothy illustrates is that you can put in the Neuralink, remove it, and be healthy, happy, and indistinguishable from a normal pig. Oh, thanks, Dorothy. Man, Gertrude, are you serious? Okay. Well, should we bring them all out or something? Would that be better? How about everyone just comes into this pen? We'll have a few, it'll be a little crowded, but whatever. Okay. All right. Well, is Gertrude still back in the thing? Yeah. Okay, we need to bring Gertrude out. Yeah. Oh, the beauty of live demos. This is a real live demo. All right. Maybe we can zoom in to do Gertrude or something. She's clearly very interested in something at the back of her pen. Can you see her? Or? Not quite. All right. All right, this might take a sec. Well, this worked earlier. All right, well. What if we lift the curtain and then zoom in? All right, here we go. Great. Okay. Great. Okay. This is a high energy pig. All right. Gertrude, thanks for coming out. So what the beeps you're hearing are real-time Neuralink in Gertrude's head. So this Neuralink connects to neurons that are in her snout. So whenever she snuffles around and touches something with her snout, that sends out neural spikes, which are detected here. And so on the screen, you can see each of the spikes from the 1,024 electrodes. And then if she snuffles around, touches her snout in the ground, or you kind of feed her some food, pigs love food, then you can see the neurons will fire much more than when you're not touching the snout. And that's what's making the beeping sound. All right, cool. So as you can see, we have a healthy and happy pig. Initially shy, but obviously high energy and you know, kind of loving life. And she's had the implant for 2 months. So this is a healthy and happy pig with an implant that is 2 months old, and working well. Yeah. All right, cool. And then we actually have, I'm not sure if this works, so we said, well, what if we do 2 Neuralink implants? And we've been able to do dual Neuralink implants in, actually I think 3 pigs at this point, and we have a couple of them here. And we've been able to show that you can actually have multiple Neuralinks implanted, and again, healthy and happy and indistinguishable from a normal pig. So, so it's possible to have multiple links in your head and have them all be sending out signals and be working well. All right. Phew. All right, so we just showed you a demonstration of reading brain activity. And let's see, probably see that. As I was saying, each of those dots represents a neural spike. And the blue chart at the bottom is showing an accumulation of neural spikes in that region. So in terms of additional brain reading activity, when we have, say, one of our pigs on a treadmill, pig on a treadmill, it's a funny concept, really. And we take the readings from the neurons, and we try to predict the position of the joints. And so we say we have the predicted position of the joints, and then we measure the actual position of the joints. You can see that they're almost exactly aligned. So we're able, with a wireless neural implant, to actually predict the position of all of the limbs in the pig's body with very high accuracy. Now, in terms of writing to the brain or stimulating neurons, we also need precise control of the electric field in space and time. We need a wide range of current for different brain regions. Some regions require delicate stimulation, some require a lot of current, and you want obviously no harm to the brain over time. And the way part of the way we analyze the stimulating neurons is with a 2-photon microscopy. I always have trouble pronouncing that, microscopy. It's very impressive technology. You can actually literally see in real time how the neurons are firing. So the red sort of things are the neurons. Red sort of flashing things are the neurons firing, or I should say the electrodes firing. So the red things are electrodes firing, and then the green are the neuron bodies responding to the current from the electrode. So you can see them lighting up different brain regions. And then by carefully controlling the electric field, you can actually have one electrode influence possibly 1,000 or 10,000 neurons. So although you might only have 1,000 electrodes implanted, you could be influencing millions of neurons. And this is just a similar chart showing stimulation at different power levels. So like I said, for the initial device, it's read-write in every channel with about 1,024 channels, all-day battery life, recharges overnight, has quite a long range. So you can have the range being to your phone, I should say. That's kind of an important thing. This would connect to your phone, and actually the application would be on your phone, and it would be communicating by essentially Bluetooth Low Energy to the device in your head. That's why I say in a lot of ways it is like a Fitbit in your skull with tiny wires. So, and then like I said, you would not be able to see the device at all. You would look completely normal and just have a small scar under your hair. And we're making good progress towards clinical studies. I'm excited to announce that we received a breakthrough device designation from the FDA in July, thanks to the hard work of the Neuralink team. So I want to be clear, we're working closely with the FDA, and we'll be extremely rigorous. In fact, we will significantly exceed the minimum FDA guidelines for safety. We will make this as safe as possible. Just as with Tesla, while it is legally possible to ship a 1-star car, at Tesla, the only cars we make are 5 stars in every category. So we actually maximize safety, and we'll take the same approach here at Neuralink. And then to emphasize again, what the goal of this presentation is recruiting. We want people who are great at solving problems to join the company and help us complete this device, take care of the animals, write the software, create the chips, and productionize everything. So we need like robotics engineers. I think we also especially need people who have worked on and shipped products. So if you've like shipped a smartwatch or a phone, or any kind of complex electronics or complex device, or advanced medical devices, we'd love for you to contact us and consider working here. So, and a very important point to emphasize is that you do not need to have prior experience on brains. So a lot of people think, well, I couldn't possibly work in Neuralink because I don't know anything about how brains work. And that's okay, you can learn, but we need software engineering, we need mechanical engineering, electrical engineering, like I said, chip design, robotics, and all the things that a company needs to work. So please send in your resume. Actually, it's not just engineering, obviously everything at Neuralink. So now let's actually move to questions. So we've piled questions that have been asked over the internet, and so we'll do live Q&A. So bring in a bunch of people from the Neuralink team. All right. All right, so if you have any questions, please submit your questions to the Neuralink Twitter account, and we will try to answer as many questions as we can over the next hour. And feel free to ask hard questions, that's no problem, and we'll do our best to answer them. All right, let's move over to the team.
Perfect. Yes, we will continue monitoring questions until the end of the event, so please keep sending them in over Twitter. Elon, do you want to come join us? All right, so the first question is, how is the spike detection implemented? Is it on the ASIC? Is it hardware and software updatable?
Yes. Yeah, I can answer that. So I'm Paul. I work. I've had a few different hats. I've worked a little bit on digital chip design, and more recently working on some of the algorithms trying to decode the signals from the brain. And the spike detection algorithm, there's historically been many ways of detecting spikes. Typically, people will record data offline and then look for characteristic shapes. But here, we're interested in detecting spikes online. And there's a number of simple algorithms that you can do, for example, like detecting just a threshold. And where we've been interested in doing a little bit better than that. So we actually look for particular shapes, characteristic shapes that we think are spikes. And so we're doing this on the chip. It's for all 1,024 electrodes. There's bandpass filtering that's happening on the chip. So if you think of these as like little microphones sending audio information, we're basically filtering all of that in real time and then looking for these characteristic shapes. You can configure what sort of shapes you're looking for, and that information is what's being sent out. The raw information coming from electrodes is way too much to send out over Bluetooth. So when you're seeing those beautiful spike rasters on the screen, those are the detections that we have coming straight from the chips.
Got it. And just for everyone who doesn't know, can you just explain at a basic level what a spike is?
So traditionally, people think of spikes or action potentials as the electrical events that happen in neurons and as the primary form of communication between neurons. And so this is a hysteresis event where you have currents that flow and generate this, you can think of it as being a digital signal, a 1 or a 0 that's being sent in time, where neurons will send that signal to often thousands of recipient neurons.
Thank you.
Awesome, thanks, Paul. So I got a question from Toby on Twitter. He asks, what can be further done to simplify the device installation progress?
So we're working on making the device as small as possible, of course, with the robot taking more and more of the responsibility away from error-prone human surgeons. We're hoping to make the process faster and safer.
Actually, it might be good for people to say, who they are and what they do.
Oh, I'm Matthew McDougall. I'm the neurosurgeon, the head neurosurgeon at Neuralink.
Thanks, Matt. Is there anything specifically from the robot that can be done to make this faster and safer and scalable to billions of people?
Yeah, I guess we've started with just implementing, robot manipulating the threads. But we definitely need to expand to essentially doing the entire surgery with the robot. So there's nothing like really, as far as I can tell, fundamentally like stopping us from doing that, sort of like at a fundamental science level. It hasn't been done in the past, I think, probably just because like volumes of surgeries hasn't been needed. But specifically for us to scale up to many hundreds of thousands or millions of patients, we will need to automate like the entire surgery essentially.
Awesome, thank you, Ian. Garrett asks, what are some of the lower bandwidth activities to target first? Is it muscle movement? Is it auditory signals? What level of bandwidth is required for effective use?
So there's a couple of...
Joey,
Just to say who you are and what you do.
Hi, my name is Joey O'Doherty. I'm a neuroscientist and neuroengineer working on decoding from the brain. So there's some low-hanging fruit that I think can really be impactful to help many people's lives, and that's restoring movement and communication in, for example, a spinal cord injured patient. And there's a lot of antecedents in the academic world where there have been very nice demonstrations of doing this. And we think we can take our technology and really bring that to the home, something people can take home with them and improve their lives.
Fantastic. Gil, there's a fun one next. All you.
Yeah, so we're fielding questions from Twitter, so there's going to be some funny comments. First question is, who are you and what do you do? I'll lead with that. And the question is, can the Neuralink chip allow you to summon your Tesla telepathically?
Definitely, of course.
You heard it here first. That's a definite 100%. Carlos, that is the answer.
It's just one bit of information.
Yeah, it's very easy. That's an easy one.
Actually, Max, this might be a question for you. Like some of the questions we had on Twitter was, how do you see the Neuralink device and the essentially API growing over time and allowing developers to interact with the device?
So there's interesting questions long term about whether you do decoding on head or on a phone or on a computer. Ultimately, so at 1,000 channels, it's possible to send all the spike data to a phone and do processing there. As this gets bigger and bigger, you're going to be more constrained by the radio, so you're going to want to push more of this on head. And that changes your programming model. But really, the APIs you're getting either bin spikes, or you're getting raw waveforms, and that's like, you can.
Yeah, it's worth noting, like the lossless compression of the data stream is about 100 kilobits with 1,024 channels.
Excellent. So this one came up a lot, and this particular question is from Yosef, but will this technology ever be used for gaming?
Yeah, probably.
100%.
Yeah, 100%, yeah.
I think that a good benchmark of does it work well in humans is, can a quadriplegic, does it work well enough for them to play StarCraft? I think that's a good functional target.
Yeah. For sure.
Yeah.
Awesome. We'll pull out back from the Twitter questions that are kind of funny. This is a question for the efficacy of the device. Right now, is the device limited to surface layers of the brain only, or can we go deeper? And if not now, what's holding us back from going deeper into the brain?
We are planning on modifying the device and the robot to be able to sew into arbitrary depths of the brain. Right now, we're limiting ourselves only to the cortical surface because that simplifies many of the problems involved with going a lot deeper.
And what kinds of things can you solve on the cortical surface versus when you go deeper?
Sure. So a lot of the low-level processing happens in the cortex in terms of motor intentions, sensory information that comes directly in. So your hearing, your auditory percepts, your visual processing, a lot of that happens in the cortex.
I mean, you could solve blindness.
Yep.
You could solve paralysis. You can solve hearing. You can solve a lot just by interfacing with the cortex. And to be clear, we actually do insert, I guess, about 3 or 4 millimeters into the cortex. So these electrodes are sensing from multiple layers within the cortex. There are deeper brain systems that are underneath your cortex, like the hypothalamus, and I think that is something we'd want to interface with for sure, because that's going to be important for curing things like depression, addiction, that kind of thing, anxiety. But yeah, like I said in the presentation, overall we're aiming for a general purpose device. Really, the thing that would change from interfacing with the cortex versus deep brain systems is kind of the length of the electrode. So we just need kind of longer wires and to adjust the robot in order to access deeper regions of the brain.
Awesome. Ian, did you have
even now,
anything
I'd
to
say the
add?
robot is designed, like the full length is like 7 centimeters or 8 centimeters.
Yeah, so right now we're designed for like 6 millimeters. The actuator itself isn't actually limited to 6 millimeters and go much deeper. That's sort of in addition to scaling out sort of to the rest of the surgery, also scaling to deeper, which is mostly a sensing problem. So the ability to avoid deep vasculature is sort of an interesting problem that we're working on in the robotics world here. So yeah, lots of cool problems in the robot.
And you're leading robot engineering.
Yeah, sorry, I'm Ian. I lead the robotics program here.
Robot is a man's best friend. All right, next question is, what is the most challenging problem that must be solved in order to meet Neuralink's ultimate goal?
Well, I think one of the hardest problems is kind of, I'd say, material science and especially the installation of the electrodes. What would you say?
Yeah, absolutely.
Also, you want to introduce yourself?
So I'm Felix Deku. I currently lead the microfabrication team. My team makes up of a group of process engineers and material scientists. And our job is to make the tiny wires, as Elon referred to them, what we call the threads that are implanted in the brain. And of course, the threads are made of conductors and insulators. And choosing the right material that is amenable to the brain and compatible to the brain is something that our team have expertise on, and we work seriously on interface engineering just to make sure that our layers are actually well thought through, well designed, and at the end of the day, when we implant this device, they'll be actually functional for either reading or for writing in the brain.
Yeah, and I think it's going to be important in terms of material science problems is making sure that the threads, the electrodes can last for decades in the brain, which is a tricky thing because it's a very corrosive environment, and you're in a dichotomy where you want to read and you want to sense electrical signals and you want to generate electrical signals, but you don't want to corrode the electrodes over time. So you need to have an insulating layer that is very robust, but also very, very thin. It has to be just the right amount of insulation, and it has to stay that amount of insulation over time. So this is why I think we think probably like a silicon carbide type insulator is probably the best long term from a material science standpoint. But silicon carbide is a tough material to work with, but that's probably the right choice long term. Would you say?
Yeah, I totally agree. And it's also, apart from its electrical properties, it also helps with adhesion between the metal layers and the polymer substrate. Another thing that we're also looking at is, since we're actually reducing the electric dimensions, the electric side, the actual side that actually speaks to the neuron, also have what we call high resistance to the signal. So we actually look into like material engineering that will reduce the impedance at that interface, so that we can actually have a very small electric side but still be able to speak clearly to the neuron.
And when you guys say thin, how thin?
Yeah.
How thin? So one strand of your hair is about 100 microns in diameter. We can think about dividing that into 20. So one of the thickness that we're working on is about 5 microns, and we have this possibility to go even thinner in the nearest future.
Yeah, we think we can probably go sub-micron in thickness, but obviously, as the thinner you make the wire, the harder it is to sense the signal and to do stimulation, because there's less cross-sectional area for the current to traverse. In terms of upgrades, that's part of why I wanted to show the explanted pig, is to show that you can actually take the device out, and there's no observable behavior change. The pig is as happy as before and healthy, and I think this is going to be important for upgrades, because obviously if you get an early device, then by the time, let's say you get version 1, probably by the time we have version 3 or 4, you want to upgrade. You wouldn't want version 1 of a phone, and 10 years later everyone's got version 3 or 4. So it's going to be important to be able to remove the device and upgrade it over time. So, so over time, the Neuralink would do even more than it did before.
Awesome. So here's a question about the device. We have been talking a lot about read speeds and we haven't talked about read or write speeds. DJ, what are the read and write speeds of the device, if you think of it like a computer?
Sorry, when you say speed, what do you mean?
Like, how quickly can you read information from the brain, and how quickly can you write information in the brain?
Okay, so one of the things to highlight is that we...
Well, DJ, what do you work on?
Yes, my name is DJ Sa. I'm leading implant electronics development.
Like a chip design.
And a chip designer, electronic engineer. So the prototype that we were showing, it has 1,024 channels. All of those channels are capable of recording and also stimulating. And in terms of recording, as Paul mentioned, we do have on-chip algorithms to do a level of compression and extracting the signals of interest, in this case, spikes, neural spikes.
Sure.
And those things are actually happening at a much faster speed than your brain even is processing those information.
Well, do you want to say like things like time resolution, like you know, within how many milliseconds can you detect a spike, and what's the, you know, just some technical data?
So in terms of the signals that we're collecting, you know, we're digitizing them at 20 kilohertz. Generally, the signals of interest are anywhere between about a millisecond in width, and so we sort of sample it at 20 times that speed. And we have analog to digital converters that divides that into 1024 levels, so 10-bit resolution. And the spike detection is done in less than 900 nanosecond, which is really, really a fast time. And it's only sort of determined by the speed of the clock. And for making sure that our implant is low power, we're running them actually at a very slow speed. And then for stimulation, you know, we can actually create any arbitrary waveforms with about 7 microsecond of resolution. So basically, whatever you want to draw, we can stimulate and generate those pulses through any combination of our electrodes.
And this is just version 0.9, or you know, aspirationally version 1. As we go to version 2, 3, 4, these things will expand, I think, ultimately by orders of magnitude, many orders of magnitude.
Great. Everyday Tesla asks, how big is the Neuralink team, and how much do you expect it to grow in the near future?
We're about 100 people right now. I think over time, there might be 10,000 or more people at Neuralink. So I think, yeah.
Couple orders of magnitude?
Yeah, exactly. A couple orders of magnitude. Those are my favorite phrases. Yeah, just, you know, a couple orders of magnitude is no big deal. Yeah, probably the number of electrodes will grow with the number of people at the company.
Hopefully that's a super linear relationship.
Yeah. Well, we might need a million people at the company then. Yeah, super, yeah, even more. Yeah. Ideally, like, yeah, super linear.
Our hiring quotas are determined by our channel counts.
Yeah. Maybe it's 10-to-1 ratio or something.
Yeah.
Cool. So Twitter asks, how does the implant system fare against various disturbances from the outside, like electrical, magnetic, Wi-Fi, radio?
Yeah, so the current version of the implant that we have is using Bluetooth low energy radio. So similar to any Bluetooth devices that are out there, you know, they are able to coexist with other devices that are using and sharing our same spectrum in 2.4 gigahertz. Obviously, as you imagine, you know, when you go to concerts or there's just a lot of people, the signal quality does degrade because it is a pretty congested spectrum. So we are actually working on some new versions of the radio that are operating at different frequencies to be able to also send out a lot more data and have it be scalable to, you know, millions of electrodes. And then also in terms of sort of electromagnetic compatibility and interferences, obviously it's very important for us to coexist with other systems and just disturbances out there. So there are lines from FDA that we'll be following and doing a lot of testing for.
Fantastic. We are going to take an audience question. Fred, take it away.
So we all want to play StarCraft using Neuralink, but what are some likely firsts?
Well, I don't know if we all want to play StarCraft.
There are other games.
There are other games to play, exactly.
But also StarCraft.
So our first clinical trial is aimed at people with paraplegia or tetraplegia, so cervical spinal cord injury. We're going to enroll, we plan to enroll a small number of patients to make sure the device is safe and that it works in that case.
Yeah, so actually just to elaborate on that, if somebody is like a severe spinal cord injury, to the degree that they have very limited control even over their facial muscles, then but with this implant you can actually think just by thinking you can output words, and you can type, and you can control a computer, control a phone, and which is pretty wild. And I think something that's very exciting as a long-term application is if you can sense what somebody's trying to do with their limbs, what they want to do with their limbs, then you can actually do a second implant that's at the base of the spine, or wherever, just after wherever the spinal injury occurred, and you can create a neural shunt. So I think long-term, I'm confident that long-term it will be possible to restore somebody's full body motion. So if somebody even has a severed spine, they will be able to walk again. They will be able to use their hands. And like when you have a severed spinal cord, you essentially have broken wires. And so if you can just jump over those wires and transmit the signals over those wires, you can give somebody the ability to walk again, naturally.
So DJ, you talked about outside interference. Can anyone talk about the inside interference? So how to protect the implant from the body?
Sure, I can talk about that. My name is Robin. I'm a mechanical engineer, and I lead the implant mechanical packaging and assembly team. So actually making the devices and designing the seal. So yeah, the body's not a friendly place to be. So what we do is basically create an accelerated test chamber that can mimic the conditions that the devices will see in the body, and basically test the devices at as fast as accelerated rate as we can. At this time, we're limited temperature-wise by some of the electronics components, but basically we can test subsystems to mimic the environment in the body, and by that we've brought some devices in the tester right now to almost a year, and all the implanted ones prior to these implants, we had tested the same architecture in the tester to validate it. And yeah, so there's obviously chemical things attacking the implant. There's pressure. There's mechanical shock and vibration. So all of these things are part of it. And yeah, well, I think one of the things that really helps is having everything in-sourced in-house. So we have the capability to deposit thin layers of metal. We have the capability to weld glass and machine micron scale with lasers. And yeah, so basically we have all the tools in-house to be able to design any sort of sealing, enclosure, packaging that we need to do.
Awesome, thank you, Robin. Another question from Twitter, will you be able to save and replay memories in the future?
Yes, I think in the future you'll be able to save and replay memories. I mean, this is obviously sounding increasingly like a Black Mirror episode, but well, I guess they're pretty good at predicting. But yeah, essentially, if you have a whole brain interface, everything that's encoded in memory, you could upload. You could basically store your memories as a backup and restore the memories. And ultimately, you could potentially download them into a new body or into a robot body. The future is going to be weird.
Cool. So I can't help but notice that the pigs back there are pretty well behaved and pretty darn cute. Can anyone talk about, I'm looking at Autumn over here. First, can you tell everyone who you are and what you do here? And can you describe, like, how are they so well behaved and so smart?
Well, I'm Autumn, and I lead our animal care program. And our philosophy here is to set up a system where the animals are able to volunteer, to make choices, to participate in our projects. As you see, sometimes they choose not to participate, and that's okay. We want to make sure that our animals are happy and healthy. So all of the behavioral research that we do is led by positive reinforcement. And again, that allows for them to choose to volunteer or not.
Sam's also on our animal care team. Sam, do you have anything to add to that?
Hi, I'm Sam, one of the veterinarians here, work closely with Autumn, taking care of the animals. And yeah, it's just emphasizing what Autumn said, the whole animal care program here, in fact, the whole company here is very dedicated to promoting the care of these animals. Everybody's involved, everybody's very interested in making sure that they're taken care of. And yeah, the program from top to bottom is designed to make sure that they can express their species-specific behaviors, choose to do things. We don't force things upon them as much as possible. And yeah, that's why you see the pigs happily rooting around the straw right now and generally being very content.
They do have those natural little smiles on their faces, which is ever delightful. Next question is, what programming language are you guys using for developing the device?
Several. Yeah, we use several different types of programming languages. So for chip development, a lot of Verilog for doing low-level programming at the kind of the register transfer level. As you go up higher and higher, there are various C, C++, Python. But to be honest, like at the end of the day, it's not which programming language do you know how to use. It's do you know the principles behind coming up with just methods to enable these systems to work. So I think if you have any experience in programming and you've been building things since you're little, you should really come join us.
Yeah, but can I play Crisis?
Eventually.
It can play Crisis.
Cool. Crisis confirmed. And then Ian, what about Ian, what about the robot? What kind of programming languages and tech stacks are you using over there?
I mean, sort of just reiterating what DJ said, sort of doesn't matter. Like specifically for us, there's a real-time low-level platform, C++, some Java and Python scripts. But really, those are more just like pragmatic choices to essentially optimize for getting like productive work done. So it doesn't really matter what your background is or necessarily what the tools you use are. It's more just can you like accomplish things really quickly.
Awesome. This next question is from This Is Rex. They're wondering, can this device be used to explain consciousness? In the long term, of course.
I can certainly shed some light on consciousness.
So, this is a really interesting question. I think the answer is yes. And I think one of the reasons that consciousness is so hard is because like anything in physics, you're looking at a mapping from X to Y, where X is what's happening then physically, and then Y is this phenomenal state. And historically, we've been unable to observe the neuronal correlates very well. And unless it's in you, we've been unable to observe the phenomenal state. So as soon as neuroscientists are able to personally get these tools where they can see the correlates and they can have the experience, I think the hard problem will vanish very quickly.
I mean, what I find remarkable is that the universe started out as like quarks and leptons, we'll call it like hydrogen, and then after a long time, well, what seems like a long time to us, the hydrogen became sentient. It gradually got more complex, and then but we were basically hydrogen evolved, and somewhere along the way, that hydrogen started talking and thought it was conscious.
I like the joke that it turns out that if you bombard Earth with photons for long enough, it'll emit a Tesla.
Exactly. Yeah, that's exactly what happened.
Just basic science, guys.
Yeah.
It's
That's
just
what they
science.
teach you in school. So there's a lot of Twitter comments coming in about a question that I think is on everyone's mind, no pun intended. What is the security of the device look like? What kind of precautions are being taken, and what does the future look like for the security of the system?
So first and foremost, privacy and security are top priorities at Neuralink, especially given the sensitivity of the data that we're collecting. And one of the things that we're ensuring is to make sure that a lot of the interactions with the brain data is going to be encrypted and authenticated properly. And I think this has been kind of a sort of recurring theme, but one of the things that we have the ability to do at Neuralink is that we work on every layer of the product, from chip design to source code, and it really gives us a unique opportunity to embed security as part of our design from the get-go, and to make sure that there are no single points of failure. So as an example, we can actually completely isolate sensitive modules like the BLE radio by just segregating it out at the hardware level, and really making sure that we protect the I/O to the brain away from any potential attacks, and really minimizing the attack surface. And we have in-house security expertise, and we're also working with external parties to do audits and perform penetration testing.
Excellent. Thank you, DJ.
Well, actually, is there a point that anybody here wants to make that has not been asked in a question, but you think should be a question? Anyone? Yeah?
So, hey, I'm Zach. I work on the microfabrication team. I help making implants. And one thing that I think is really cool, just in general, is that this is a platform, essentially, so we can change the design up in a variety of ways. So if we find that a certain design or electrode size or number of electrodes works better in different areas of the brain, we have the capability. That's very cool.
Fantastic. Anyone else? Dan, do you have something to add?
Yeah, I think one of the things that's allowed us to make such fast progress in the last few months is the use of pigs as a model. And we started out choosing pigs because of the very similar anatomy of their skull to humans, same thickness and similar kind of membrane, dural membrane. But then as time went on, we realized that pigs are actually have amazing other properties. You can train them to walk on treadmills. You can train them to do all kinds of tricks, and also that they have this large representation of the snout in the cortex, which you can very easily stimulate. So the question would be, why are we using pigs? And I think we've even surprised ourselves at how useful they are as a model in this respect. And another important point is that it's very easy to keep pigs happy. They have very low needs, and so we can build an environment in which they have amazingly good welfare.
Yeah,
You seem very happy about food.
Yeah, it's easy to make pigs happy. Basically, they love food. Pigs really love food. This is a true thing about pigs. Give them sort of some straw and some things to play with, and some friends to hang out with, and good food, and they're happy as pigs. And then pigs are actually quite similar to people. So that's if we're going to figure out things for people, then pigs are a good choice. And they're quite robust creatures, like little tanks. And then I think one of the questions was like, is the device itself robust? And it's like, well, pigs, they bustle around quite a lot, and they bump into things, and they headbutt each other at times, and they're pretty animated. So if the device is lasting in the pig, as it lasted there for 2 months, and still going strong, then that's a good sign that the device is robust for people.
Fantastic. One common theme that's been coming up a lot on these Twitter questions coming in is that of availability. And so Matthias has a specific question on this, which is, any estimate of how much it will cost at launch and what price it will reduce to over time?
Well, I think at launch, it's probably going to be, I would say that's not really representative, because at first, I think it's going to be quite expensive, but that price will very rapidly drop. And I think over time, we want to get the cost obviously down as low as possible. But I think inclusive of the automated surgery, I think we want to get the price down to a few $1,000s, something like that. And I think that's possible. I think it should be possible to get it similar to LASIK, and then the device electronics itself, I think will not be very expensive, because it actually does use a lot of the parts that are made in extremely high volume, in tens of millions of units,
for smartphones and smartwatches and wearables in general.
Great. So here's another question about the device. What does the architecture look like? Is it a CPU? ARM CPU? What's going on inside the device that you can talk about, DJ?
I can talk a little bit about the digital architecture. It's fully custom. One of the most difficult challenges, I think, of building an implant is the energy density. So the more electrodes you record from, the more energy you're going to be consuming. And so there was nothing commercial out there. So there's an analog front end that's able to amplify these really small signals, like microvolt range, so that we can actually digitize them, and then take those signals and then find exactly what we're looking for. And there was nothing out there that could basically do those two things. And so that's why we had to build a full custom ASIC. And so there's really, there's nothing out, like it out there. It's designed specifically to record signals from the brain, and anything else would just be wasting energy.
Yeah, so the thing that I would add to that is, so there are obviously elements that we customize from ground up, like our neural amplifiers and some of the algorithms that we develop, but a lot of the other systems around it are really borrowing from parts that are already been productionized and available from the wearables industry. So BLE radio, a lot of the low power microprocessors that are part of it, a lot of small sensors. So there are obviously the neural sensors that we're developing that gives us kind of a unique data set for our applications, but really a lot of that is getting packaged up and just not really resisting the industry that's been sort of been laid out to create these devices with very short amount of time.
So here's another question about the integrity of the device, more from a mechanical perspective. So you're replacing a piece of bone and replacing it with an implant. And then the person is going to take that home. How does the integrity of the device fare compared to, I don't know, bone or something similar?
Sure. Well, I think Matt's probably replaced a lot of pieces of skull with plastic and other materials. So I don't know if you can talk about some of those. But yeah, basically, I mean, we know that what the mechanical properties of bone are, and we know what the stresses on the device are going to be. So it's fairly easy to just go from first principles and design for any condition that it might see.
Yeah, I mean, as you can see from the pigs, as I was saying earlier, the implants are obviously very robust because pigs move around vigorously, they roll around, they bang into the wall, they bang into each other. They do like headbutting, and way more than people do. Well, sure. But like it's not like the pigs are just walking around very delicately. They're high energy creatures, and I think it's clear that the implants are has been going for a few months, still going strong, despite a lot of vigorous activity from the pig. And it's difficult. You can't just explain to the pig, hey, you've got an implant in your head. Why don't you take care of it? So it's got to be robust against a lot of head impacts, essentially. So, I think maybe one of the things that isn't super obvious is that the implant itself is attached to the skull, but the electrodes have long threads, so you can have quite a lot of movement, relative movement between the brain and the skull, without putting attention on the electrodes that are inserted in the cortex. So, well, let's see. With that, maybe a couple more questions, or if anybody wants to make some comments, and then we'll call it a day.
So I just want to add to what you just said. So the thread is actually also in the brain, also because of their thinness, they're actually very flexible. And so as the pig is moving around and banging their head, the threads actually move with the brain, even the normal pulsation of the brain. And that helps minimize stress within the brain tissue also. And that has a long-term impact on the functionality of the device.
Zach, how long are the threads?
Well, right now they're about 43 millimeters, but like I said, it's tunable. So if we want to hit deep brain regions or some other brain area, like we totally can do that.
Just to follow up on what Felix said about the threads moving around with the brain, I mean, that's great for protecting the threads, but it equally serves to protect the tissue around it. We have a lot of different ways to image the tissue around the threads and iterate very quickly on doing things to them that will improve the overall biocompatibility.
As a closing question, I thought we might go down the line starting with Dan. And what I'm wondering is, what is the #1 thing on your wish list that you're really hoping that the Neuralink device will do over time that you're working towards?
So my background is in visual neuroscience, and one of the things I think has great potential for the Neuralink is to provide a visual prosthesis for people who have retinal injury or blindness through eye injury. You can essentially plug a camera directly into the visual cortex and stimulate with an enormous array of thousands or maybe tens of thousands of electrodes to recreate a visual image. And in time, perhaps you can use that same technology in people who haven't lost vision to produce some kind of heads-up display, something like Terminator or something like that.
Wonderful.
In fact, it's worth saying that, like, over time, we could actually give somebody supervision. Like, you could have, like, ultraviolet or infrared or see in radar. Basically, name your frequency. You can just dynamically adjust the sensor or have sensors that feed into the visual cortex across a wide range of frequencies and actually have superhuman vision.
Yeah, so for me, telepathy. So I think it's incredible amount of effort to put your thoughts into a set of words, and it comes out completely compressed. So being able to do that seamlessly without being able to compress it with all of the mechanisms would be great.
Yeah, it's like just I'm sorry, to add further to that. In fact, when I did the Wait But Why article, I think Tim thought I said consensual telepathy, but I said conceptual telepathy. I would presume it would be consensual, because you definitely don't want just people, sending stuff into your brain without your consent. But a lot of our brain thought capacity goes into compressing our thoughts into words. And then you think of like the data rate of words. Words are a very low data rate. And we're putting a tremendous amount of mental energy into compressing the concepts and thoughts in our head into words, and then slowly talking. Speech is so very, very slow. And we could actually send the true thoughts. We can basically have far better communication because we can convey the actual concepts, the actual thoughts, uncompressed to somebody else.
So non-linguistic, consensual, and conceptual
Yes,
telepathy.
exactly. Non-linguistic, consensual, conceptual telepathy.
There we go.
Rolls off the tongue.
Yeah, I've actually been excited from the beginning sort of about the side benefit of these devices. I sort of see them as essentially like an oscilloscope to a printed circuit board is our device to the brain, where just by virtue of having this in there and being able to see what's actually going on, you'll end up learning a ton about how the brain works. And so sort of augmenting people, but also just using that to learn a lot more about like neurological diseases is really exciting to me.
Absolutely.
So to sort of follow up on Elon's thought, I feel, and I imagine a lot of other people feel the same way, that there's a lot of sort of trapped creativity in your mind. You can, for example, close your eyes and conjure up like an incredible, like Dali-esque scene. But if I wanted to actually show someone that, it would take years of honing a craft to be able to paint that. And so, potentially with enough electrodes in the right places, you could begin to sort of tap into those raw concepts or thought vectors and be able to decode that and show people. It could be for, art, you imagine music, or even for like engineering, like a three-dimensional model. And like.
So mental artistry is a new field.
I like to think about ways to interface devices with biology better. And so one of the things I'm looking forward to is getting this thing to be less like technology and more like biology, so that it really is seamlessly interfaced with the brain, stable for a very long time. And then similar to that, having stimulation be much more precise and multidimensional, such that eventually the brain sort of doesn't really know if it's being stimulated from outside or inside, and You end up just sort of completely merging.
Wow.
Yeah, you know, following up on stimulation, you know, one of the things our device can do is simultaneously to use that.
Yeah, I'm excited just because of the scalability of the device. We're doing everything in-house, and all of it can scale to more channels, more brain regions, etc. I think, yeah, I'm really interested about solving things related to anxiety or depression, or even like removing fear. Like I'm an athlete, and to like rock climb without fear would be pretty.
Maybe you need a little bit of fear.
Yeah, just a little. And also, it'd be great if we could make the pigs fly, but
It's the next step.
I think we have an incredible opportunity to limit human suffering to a tiny fraction of what it is today in all kinds of different avenues. Pain being the essence of suffering, we might be able to control that finally. And so many other diseases, so much other suffering in the world, I think the Neuralink device could help a lot with.
Amazing.
I think all these things are great functions for a Neuralink. I think on a species level basis, I think it's going to be important for us to figure out how we coexist with advanced artificial intelligence, and I think achieving some kind of AI symbiosis where you have an AI extension of yourself, like a tertiary layer above the limbic system and cortex, and having that symbiosis be good, such that the future of the world is controlled by the combined will of the people of Earth. I think that's obviously going to be the future that we want, presumably, if it's the sum of our collective will, and so I think it's going to be important from an existential threat standpoint to achieve a good AI symbiosis, and that's what I think might be the most important thing that a device like this achieves.
I have, in many ways, a very basic science interest, which is I'm really interested in the nature of consciousness. And there's a lot of very silly philosophy that's been written about it over the last 1,000 years. But I think that we've been very limited by the tools and our ability to interrogate and measure the brain. And as these tools get better, it will pull it into the realm of physics. And it's really one of the last big, great mysteries in science.
So for me, can you imagine a disease-free future? A future where you know what's going to happen to you before it happens, so you can prevent it. With these devices, we'll be able to not just pick up electrical signals, but we can also pick up chemical clues in the brain. And if you're successful, which I know we are, we'll be able to kind of prevent ahead of time, diseases. And really, the functionality of this device is widespread. So I'm looking forward to the future.
I'm really excited about the opportunity to help people overcome challenges that they face through life circumstances, bad luck, through no fault of their own, spinal cord injury, brain disease, some devastating things that completely change your life. Hopefully we can help them get some function back.
I know and love many humans with autism spectrum disorder. So I'm really interested to see how the Neuralink might be able to support them if they chose to do that.
Yeah, so I mean, everyone else along the line has had amazing ideas and suggestions. And yeah, for me, it's about memories, and everyone loses those memories over time. I already can't remember what happened to me when I was younger, and it'll only get worse. And so having a repository of memories that you can access whenever you want. If you're feeling down, you can go access some good memories. If you miss something or you miss somebody, you can go and access those memories. And I think that would just be such a life-changing experience to be able to just tap into that.
Those are such a beautiful and diverse array of answers there.
Yeah. All right. Well, thanks for tuning in. And as I said, please consider working at Neuralink and helping us solve these problems. There's a tremendous amount of work to be done to go from here to a device that is widely available, and affordable and reliable. So please consider joining us and supporting us in our mission. Thank you very much.